Okay, thank you very much. Time to welcome our next speaker, Jonathan, who's going to tell us more about Asyncio.
Okay. Thank you. All right. So good afternoon. Hope you have a good FOSDEM. So I'm going to talk. You cannot hear me?
So speak louder.
Okay. Can you hear me? Yeah, good enough. Okay, I try to speak loud enough. Okay, so we are going to talk a bit about async I/O in Python. So it's about the async and await keywords that were added a couple of years ago and how we can use them within Python. And a bit about what is the difference between writing async I/O code and writing threaded code, because that's another way of doing concurrency. So all this is about how can we speed up our program, how can we do things in parallel in order to improve the execution speed. So we have quite a bit of different ways of doing concurrency in Python. First, there was multi-threading, which is the easiest way to do concurrency. Then there was multiprocessing, which solves an issue if you need more CPU, because one Python process can only consume one CPU. If you need to have multiple CPUs, because your problem is very CPU intensive, then you need multiprocessing. Then there's G-events, not going to talk a lot about that. And then you have a whole lot of event loop-based implementations. Like there's Twisted, which is probably the oldest. Then there are a few others. And in 2012, we got async I/O. So let's first start with threading. So threading is pretty easy. You define two functions, in this case, Alice and Bob. And then you create two threads, where each time you say first the entry point, the target is Alice. Second time you say target is Bob, and you start them. So if we execute this, then you see these two things are running concurrently. You see Bob print statements there nicely interleaved. Now, things become more complex if these threads, if they have to coordinate with each other, if they have to exchange data somehow. Like, for instance, in this example, you see that there's a global variable counter, and both threads are trying to manipulate that variable. So first we are doing an increment, and then we are doing a decrement. And both threads, you see, they're doing exactly the same thing. And now we can try to execute this. So what you would expect is that for every increment, we do a decrement. So if we would print the value of counter at regular points in time, we would always print the value 0, 1, or 2, depending on when exactly we print the value. So let's try that. That's this script. You see, it's not exactly the case. Right now, we are printing negative values, then it becomes positive again. And as we go on, we diverge more and more from actually the 0 value. So how is this possible? Let's take this function. So very simple function with an assignment and an increment. If we're going to disassemble this function, you can do that in Python by importing the dis library. And then you do this.dis and you pass f so that you see the bytecode of this function. Then you see that actually for the increment that corresponds with these 4 instructions, that it's not really one instruction. An increment like plus equal 0 or plus equal 1, sorry, consists of these 4 instructions. It has to do with how the Python interpreter operates on the stack. But it's very interesting. It means that if we have 2 threads that operate on that same variable, that at any point in time between these instructions, we can go from one thread to the other thread, which means that these 2 threads can possibly interfere with each other. And that's exactly what's happening in this example. So the way to solve that is by using a lock. So you can create a lock, and you surround these blocks where you modify that shared variable with that with lock context manager. And then you prevent these 2 threads from manipulating the same variable at the same time. So what is wrong, or what is the disadvantage of using threads is that as soon as you have to manipulate shared data structures, you have to think about locking. And that's something which is very hard to get right. So either you choose to use one global lock, but then you have the risk that you lock too often, like things that could go in parallel, that these things become sequential, or you use many small fine-grained locks, like for each data structure you create one lock to protect that from being modified by other threads. And then you have the risk of deadlocking. There are ways to prevent that, like some guidelines and so on, but it's very hard to get right. And then threads, they have some overhead, not a lot, so it's not really the main reason not to use threads, but still they have a bit of overhead. I should also mention that instead of using shared data structures, you can also not share data between threads, but use some kind of message passing. So these threads, they can communicate over a queue. And so if one thread has to pass data to another thread, you can send it over the queue and serialize it. That's a way to prevent using locks and prevent these issues. But it's also a whole different way of programming. So let's come to async I/O. We're going to have a look at how we can do these things in async I/O. So here we have also two functions, function 1 and function 2. And we are going to run these in parallel and do the same thing, the same increments and decrements. Now, you see that these functions are not normal functions. There's async in front of the def keyword, which means that's an asynchronous function. And then there's an await as well. Now, what the await keyword here actually means is that that is a place where it's fine to go from one function to the other. So basically, we are in control when we do the context switching between these two functions. So if we are now going to execute this, these two will run concurrently, but the context switch between these two functions, they will only happen at the place where we have an await keyword. There is a sleep that's not important right now, but it's just to make this example work. So let's this example. You see we always print 0. That's what you get when you would execute this script. So the await keyword, actually, it means that it's a place where it's safe for one coroutine to move to another coroutine. That's it, basically. Now, in practice, it means a bit more than just that. It also means that you're probably waiting for some I/O to complete, because the problem that we typically try to solve with async I/O is a very I/O intensive application. And when you have many things going on in parallel, a good point to go from one coroutine to another coroutine is when you're idle, when you're not doing anything. Like, for instance, you do a network request, you wait for the response to arrive. In between, you're not doing anything. So that is exactly the right place where it makes sense to go to another coroutine and resume the execution over there. And so actually, you will go back and forth between all these coroutines at the point where you have an await. So you have total control over the context switching. So basically, the difference between threads and coroutines is that threads, they're preemptive, and the operating system decides when to context switch. With coroutines, like what we have in async I/O, we are in control over the context switching. And that means that most of the time, we don't have to use locks, because we know what pieces of code are run atomically and won't be interrupted. That's exactly where we don't have an await. And so it's much easier to get your code right. With threading, there's a lot of chance that you get things wrong, that in production at some point things will start breaking. With async I/O, it's easier to get things right. Now, important to know is that all of this runs actually on top of an event loop. So the coroutines are an abstraction on top of an event loop. An event loop, that's a very simple mapping where you map I/O completion events to callbacks. So like, for instance, when a network socket becomes ready for reading or writing, when you receive mouse or keyboard events, these are events, and then you specify a callback that will execute when that event happens. And that's literally this while true. So you wait for a file descriptor to become ready, file descriptor maps to an event, and then you call the corresponding callback, and you keep doing this in a loop. So if you keep this in mind, then you see that we only run one callback at a time, right? And that's really the advantage of event loops. These callbacks, they won't interfere with each other. So we run everything in one thread, one callback at a time. I've said there is no complicated synchronization like data locking and so on. It's also pretty easy to debug, because if you put a break statement in your code, your whole event loop will freeze and you can inspect the state of all coroutines. And this is great also for handling many connections in parallel. Like if you have thousands of connections, like WebSockets connections, and they're idle most of the time, then event loop is perfect, because you can wait for so many file descriptors at the same time. Your operating system can do that for you. And then you execute the callback that corresponds to the incoming network connection from where you receive a message. And that is, of course, much cheaper than having one thread for every single connection. One important thing to know, though, is that you should not mix async IO code with traditional or like the typical blocking code that you find in other applications. Like, for instance, if you use the request library for doing network requests, that's what many people do in Python, they will block. You do a request and your statement will, your request.get statement will wait for the response to arrive. If you try to do that in an event loop, your whole event loop will freeze. So you cannot do that. There are workarounds to still execute that kind of code, but it's best to avoid it if you can. So we should not do blocking I/O. Instead, we should do non-blocking I/O by registering a callback in that event loop, which will then execute when a response arrives, for instance. Now, these coroutines are an abstraction on top of event loops. It's pretty nice so that you don't have to think about all these callbacks, because otherwise you would end up with very ugly code. So this is an example of what, it's really hypothetical because this library doesn't exist, but this is what a database query would look like in async IO code. So we do a query, we wait for the response because there's like a networking in between, and when the response arrives, that thing will be assigned to users at this point. So the await keyword here means that we wait for the response to arrive, we return to the event loop. The event loop can then do other things in between, and when the response arrives, the event loop will resume the execution of this function. So it's like kind of a state machine. The await will suspend it, and later on we resume it. So we do actually two things. With await, we say we can go to another function, but we're also waiting for the response. We can also use the await to call another coroutine. Like, for instance, here we have a main function and we have a getUsers function, and the main function is calling getUsers. But getUsers is an async function, which means that if you call it, you don't get a response, but actually you get a coroutine object, and you have to use await in front of it in order to get the actual result. So the await keyword is very often used to await the outcome of another coroutine. You see at the very bottom there's async io.run. That is how you start an async IO program. You need to have an event loop that gets started and that will like operate these coroutines. That's what the very last line is doing. Yeah, so async and await, they very often go together like you see in this example. Something else which is important to know is how to run coroutines in parallel, because that's the whole point of using async IO. You want to parallelize stuff. And one way of doing it is by using async io.gather. So async io.gather is a way to wait for the outcome of multiple coroutines at the same time. In this case, we spawn the getUsers coroutine twice, and when both are done, these the execution of the main function will go on. So actually, you can think of async io.gather as a join in threads. You're joining multiple things together. And actually, I like this way because of doing concurrency. I like this because you have some kind of symmetry. You have a place where you start things in parallel and things come back nicely together. That's what you actually want. You don't want to fire something and then forget about it. It's very important actually to do the join in order to get some kind of symmetry. If you cannot do that, then you could actually do asyncio.createTask that will spawn the coroutine, and the execution in the main function still goes on. But if later on you decide you need a response, then you can still await for the task. And you could actually do users equals await task to capture the outcome of that coroutine. But I think it's pretty important to actually not just spawn tasks and not wait for the response, but instead really wait for the response, because that way you can do proper exception handling. If there is an exception raised in get users, using try except, you can capture them around the await statement. Then there is also async with and async for, which are pretty nice. So the with block you probably know as a context manager. That's something, code that you execute before and after the block, very typically used for establishing a connection and closing the connection, or allocating resources and releasing resources. So that's what a with block is doing. Async with is what you do if any of these two blocks, the enter or the release, involve async code. And in this case, that's the case. Establishing a connection has to be asynchronous because it takes some time to establish the connection, and you need an async with in order to do that. Then async for is something you typically see when you're consuming asynchronous data stream. Like, for instance, you select the users from a database table. The entries are all transmitted over the wire, over the network, and you receive them in chunks, not all at once. So you don't want to wait until the whole response arrives before you start processing, but you want to start processing things as soon as possible as they arrive. So that means that every iteration of the for loop involves possibly waiting for the network response to arrive. And so that needs to be asynchronous. That's when you have an async for. And these two are typically things that you see that you have to use for many async I/O libraries. Then there are executors, which is also something good to know about. So this is something you use whenever you have to run traditional blocking code. It could be either a situation where you have a blocking I/O library, like requests, or it could be a situation where you have very CPU-intensive code. In that case, also, you would block the event loop. If you have something which is very computational expensive, you could run it in another thread and have the main thread, the main event loop, go on and respond to incoming connections. So in this case, the executor will run on another thread or on another process, and the await can still be used to wait for the outcome of that piece of code. Then one warning, don't turn every call into an async call. It's what people often get wrong when they start with async I/O, because some people think that at some point every function will become async, because at some point every function will involve doing I/O, right? And often that is the case, but doing I/O doesn't mean that you have to wait for the I/O. For instance, in the case of a logging server, imagine that you're logging to a remote server, then you don't have to wait for these logging messages actually to be transmitted. You want the logging to happen in your server, but you want your execution to go on as soon as possible. And so instead of using an await in front of your logging calls, it's best to implement your logging framework in a way that you push all your logging messages into an async queue, and somewhere else you have then a coroutine that consumes the queue and flushes the messages over the network. And so that way your functions don't have to be async, not necessarily. Something else here, which I think is important, we should try to separate the code that is doing I/O from the code that is doing computational stuff, if that's possible. For instance, if you are doing a parsing library where you are parsing data that's completely, that can be written completely independent from the I/O layer. And so if you can separate these things, then you can have code that is completely synchronous and then asynchronous code around it that calls the synchronous code. And that's totally fine. So try to avoid ending up in a situation where every function becomes async. This is next actual example. I'm not going to say a lot about this because later today, Tom Christie will talk about HTTPX, which is an async IO library for doing HTTP calls. So if you're interested in that, then stay for a few more talks, then we will discuss this. But you see that here as well, we have the async with block for establishing the connection, and then the await to wait for the response is something that you very often see with these async libraries. Then something else which is good to know is that if you're experimenting with async IO, you cannot just use an await keyword in your interactive shell. If you try that, there would be a syntax error because you can only use an await in an asynchronous function. And it's very cumbersome for trying out async IO code. But there's a solution. IPython does support async IO integration, which means that in IPython you can use the await keyword top level, and then IPython will ensure that the event loops runs, and so it's very great for experimenting. Or you can do Python-m async IO. It's also very, it's basically the same thing, but then with the normal Python shell. So to conclude, async IO is a pretty great concurrency pattern for IO-heavy applications. Not so much for CPU-intensive applications. But if you're dealing with a lot of I/O and many connections, then async I/O is great. It's not the easiest to begin with, honestly. But very often when things become more complex, it is much easier than trying to get right. And then the important pitfalls I would like you to remember: try not to mix async I/O code with blocking I/O unless you use an executor. And try not to turn every call into an async call. So that's what I have. I don't know whether there are any questions. You can find me on Twitter, on GitHub. Sorry? Yeah. This one. Gather can take as many functions as you want. It takes them as positional arguments. You can pass as many coroutines as you want together. Thank you.